So in this lesson, we're going to discuss the mathematics of population growth. And in this lesson, we will focus on linear models. Population growth is used to measure the rise and fall of many different levels, whether it's endangered wildlife populations or fishery stocks or insects and pests, infectious diseases, radioactive waste, trash, and so on. The term population growth is used in a very broad way. Originally, population growth would mean populace of the people was only used to describe human populations, but now it includes collections of any objects that may collect to increase in numbers or decrease in numbers. Again, population growth no longer just means increasing, but is also broadly used to describe decreases in population as well. So there's two types of growth. There's continuous growth. Continuous growth means that we are taking into account every hour, every minute, every second that there's change occurring. And discrete growth is going to be countable growth. So we're going to add or subtract whole numbers to the population. Another way to consider discrete growth is the growth at specific time intervals. So we used to use the word decay. Decay is still used, but still population growth, the word growth is used to describe increase or decrease. A decrease would be negative growth. But decay always means decline. So population sequences describe the ebb and flow of a particular population over time. It can be thought of as a list of numbers called a population sequence. Every population sequence starts with an initial population. That initial population is denoted with P for population and a subscript of 0, meaning the population of the 0th generation. The population sequence continues as follows. We have population at generation 1, generation 2, and so on, where P sub n denotes the population for the nth generation. Going back to the 0 notation, often you'll hear when a disease is going through a population, they talk about patient 0. Patient 0 is where the disease that is affecting the population started, or also another way to think of P0 is ground zero. So the place where a war starts or a battle starts is often referred to as ground zero. So P0 is where everything starts. So we have two types of population models that we will be looking at. There's the implicit model, which is also referred to as the recursive model. This requires previous data to generate new data. So need to know previous data to generate new data. The explicit model, also known as the function model, you just plug in an input value for the generation and you get out a population value for that generation. So you don't need previous data. This is the faster, more efficient way to deal with populations. So again, we input the generation and it outputs the population. So you might say, well, why do we have both? Well, sometimes we can only model things implicitly. We don't have enough information to model things explicitly. And a good example of an implicit model would be the Fibonacci sequence. The Fibonacci sequence is 0, 1, 1, and you always take the previous 2, you add them to get the next 1. So now we would add 1 and 1 to get 2, we would add 1 and 2 to get 3, 2 and 3 to get 5, 3 plus 5 to get 8, and we would keep doing this. And this is a sequence of populations that we cannot write a functional model for, or it is very difficult to come up with a functional model for. So we would work with this implicitly. So an implicit model requires data from the previous generation in order to calculate population for subsequent generations. The model is population for generation n is equal to population for generation n minus 1, or the previous generation, and you add to it the common difference. So if I were to have p sub n equals p sub n minus 1 plus 3, and we knew that p0 was, let's say, 7, then we can say that p1, if I plug in 1 for n, then 1 minus 1 is p0, so p1 would be p0 plus 3. We see that p0 is 7, so p1 would be 10. And then we would say, all right, p2, we would look back at the model. If n is 2, then n minus 1 would be 2 minus 1. P2 would be P1 plus 3. We see that P1 is 10, so we're using the previous generation's data to generate P2 is 13. So we can keep doing this and getting each next generation. The drawback to the implicit model is I cannot jump straight to P10. I need to calculate everything in between. So we see here there's also a recursive model for exponential growth. We're going to work with this in a separate lesson, but just to show it follows the same format. Pn is the population for generation n. We would take the previous generation's population and multiply it by the growth factor r. So we'll work more with exponential growth in another lesson, but we're just showing the similarities in what's called the implicit or recursive models. They require previous data to generate new data. So here we see we have an application. It says consider an application that grows according to a linear growth model. Once we see linear growth model, we're saying P sub n equals P sub n minus 1 plus D. With an initial population of 25, once we read that, we should say P0 equals 25. And a growth rate that increases by 7. That tells us that D equals 7. And that's all of the information that's outlined here. So as we were reading it, we identified each of these three components. Now, the problem says write a recursive model and find the population for generation 2. So here is our recursive model. It is important to note that P0 and D are both stated. Now to find generation 2, we know the population for P0. We have to find the population for P1, and then we can get the population for P2. Remember, recursive models require all of the in-between years to be calculated to get to the result. So now we say, well, let n equal 1. When n equals 1, then Pn becomes 1, and Pn minus 1 becomes P0. And we look up at P0 from the previous generation, which is 25. We plug that in, and 25 plus 7 gives us P1 is 32. And now we say, all right, let's work on the next generation, n equals 2. We plug in 2 for n. We see that that's P2 equal to n minus 1 is P1. We look up P1 because we've calculated that. It's 32. We plug that in. And we see that the population for generation 2 is equal to 32 plus 7. That gives us 39. Now, we can also rewrite the linear models from recursive form to explicit form, and an explicit model is also known as a function. So that means we have input values and output values. We don't have to calculate all of the in-between generations. If we can write the explicit model, it becomes faster and easier to use. So suppose we have a population of Demarest that was 4,900 residents in 2012, and it increases at a rate of 5 per year. We want to write an explicit model. We're going to say let n equals 0 be the year 2012. So that means that my P0 is 4,900, because that's the population for 2012. And we're letting 2012 be the starting population that we're tracking this for. So find the population for the year 2020. Well, how many years after 2012 is 2020? This means that P8 equals the population in 2020. So the explicit model is P of n equals P0 plus D times n. We've established that P of 0 is 4,900, and it's increasing at a rate of 5 per year, so the D is 5. And this is our explicit model, or our function. Now we want to know the population for 2020. Well, that's 8 generations after 2012. So plug in 8. We see that P of 8 is 4,900 plus 5 times 8. We get that P of 8 is 4,940. Population in 2020 is 4,940. So part of this is making sense of the subscripts. Instead of having a subscript of 12 and a subscript of 20, we used a subscript of 0 and a subscript of 8. We also want to be able to convert from implicit models to explicit models. We can do this with linear functions very easily. We can't do this for all models that we'll encounter, but for linear models, we definitely can. So we see it wants us to convert the implicit to explicit. We see that the implicit has a P0 of 103 and a common difference of -2. We just have to remember the format for the explicit model. And we're going to plug in 103 for the initial population and -2 for the common difference. And we can now write the explicit model as 103 minus 2 times n. Similarly, we can take an explicit model and convert it into a recursive model. So here we understand that the number multiplying n is our d value. That means the constant being added to it is our initial population, P0. And we would write the formula for recursion, which is P sub n equals P sub n minus 1 plus d. P0 equals 11, and d equals 7. And this would be our recursive model. We could simplify it a little bit more. By putting the d value in, because that doesn't change, but we still leave the initial population P0 outside of it because these numbers are both changing for different populations. Again, if I were handling n equals 2, we would say P2 equals P1 plus 7. I don't know P1, so I would have to figure that out before I can move ahead to P2. Right. So that's the end of our presentation. Go back, watch the video again, take notes, and then complete the practice.